where maximum 2 dots per side, but this time we're dealing with covalent compounds. So we're not giving up or taking electrons, we are sharing electrons. So first of all, let's remind ourselves a little bit about covalent bonding, both pure and polar. We ask ourselves, is there metal? We're going to say no most of the time. We saw some yesterday where the electronegativity values ended up being different enough that it was polar, even when it was a metal. Okay, so remember we need to use our prefixes. The prefixes that people get wrong the majority of the time are tetra through hexa. So those are good ones. If you don't have these memorized yet, make sure to focus especially on those so you don't get them flipped around. Okay, we're going to end with the IDE at the end like we do with ionics. So C3H8. What do we get with C3H8?
Isn't it tricarbon
Close. Okay. Octahydride. If it was hydroxide, we'd have OH.
Okay.
Good, good. Many people do that. So tricarbon octahydride. Thank you. Okay, SiO2. What would that one be called? Yeah, silicon dioxide. Now the question is, why don't we use mono to start it off? It's because we never use mono on the first word, even if it is just one of them. Just a little reminder for us there. So silicon dioxide, thank you. Okay, we're not looking at charges at all, so we're just going to take whatever our prefix was and put it directly behind the element symbol. So if we have carbon tetrachloride, I have 1 carbon, 4 chlorines, so I have CCl4. Disulfur dichloride. S2Cl2. Can I just call it SCl? I cannot reduce the way that I did with ionic because we're not having that big 3D molecular shape of all of the sodiums and chlorides that we had before. Here it is actually 2 sulfurs and 2 chlorines bonded. So we never reduce when we are dealing with covalent molecules, either pure covalent or polar covalent. Okay, so Lewis structures. We're going to be dealing with a lot of Lewis structures when we're dealing with covalent bonding. And they show us what bonds we have, because it's going to show us all of the valence electrons. And remember, with covalent, they are sharing electrons. So we're going to show sharing, not giving up and taking. To draw them out, we figure out first the total number of valence electrons within the molecule. That's going to be our final check. We want to make sure that we have the amount that we expect to have. We determine which the central atom is, and the central atom is the one that requires the most electrons. And we are shooting to fit with the octet rule, so where we're finding the isoelectronic series that matches up with the nearest noble gas. We want to make sure that every atom has 8 electrons around it, except for hydrogen. So again, we imagine that we have a box. Within that box is our symbol. Let's do SY for symbol. And then we can have up to 8 electrons around it. Again, these are going to be the valence electrons only. And we don't actually draw out the box, but just so you can see, the maximum per side is going to be 2. Some teachers teach where you have to do it in order. So 1, 2, 3, 4, 1 on each side to start with, and then you start again at the top. 5, 6, 7, 8. That's helpful. Not necessarily necessary, but it's helpful. So if you get in the habit of putting them around that way, it can be easier for you to see some of the patterns that we have. So let's try one. We have, phosphorus trifluoride is. How many phosphoruses do I have? Shout it out. 1. How many fluorines do I have? Shout it out. 3. Excellent. So PF3 is the symbol. Well, I want to know how many total electrons I have, so let's break this apart. Phosphorus, if I look at my periodic table, has 5 valence electrons because of where it is. We could do that a couple of ways. We could start looking at the alkali metals and count over. That gets us to 5. We could write out the electron configuration to figure out how many valence electrons it has. We could have memorized that that column is always 5 valence electrons. Multiple ways to do it. Fluorine. There are 3 fluorines, and each of them have how many valence electrons? 7, yeah. 7 valence electrons. So my total that I'm going to be checking for is how many? Yeah, 26. I'm going to look for 26 total electrons on my diagram. How many more does phosphorus need? 3, yeah. How many does each of the fluorines need? 1, yeah. Okay. So which one should I put at the center of my diagram? Phosphorus, absolutely. So I'm going to put my phosphorus in first. And I'm going to draw 5 electrons around it because it has 5 valence electrons. So I'm going to start up here. 1, 2, 3, 4, 5. 5 valence electrons to start out. I'm going to put a fluorine next to it. We're dealing with covalent bonds, so they are going to be sharing 2 electrons. 1, 2, 3, 2, 3, 4, 5, 6, 7. Okay, they're going to share 2 electrons. We can see these 2 right here. I'm going to clean it up a little bit. And, cleaned it up a little too well. Okay. We say that the phosphorus and the fluorine are sharing 2 electrons. And we do that by drawing a line. Each line represents 2 electrons being shared. Electrons being shared. So we wouldn't do lines for each of the 2 around the fluorine or the extra 2 around the phosphorus because those aren't being shared. The lines represent those electrons being shared. Well, I don't have all 3 fluorines out around my phosphorus yet, so I'm going to put another fluorine down here. 1, 2, 3, 4, 5, 6, 7, and we'll clean it up. And that electron from phosphorus and the electron from fluorine are going to get shared. So those 2 electrons are being shared in between them now. And then my last fluorine is going to go over here. And I put that way far away. It didn't mean to be. And they will share those 2. So now I need to do some of my checks. First of all, I want to see if I have a total of 26 electrons. So I can count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Sure enough, I have 26 total electrons. Yeah?
So, does it always share 2 electrons?
Not always. Yeah. Good question. Now I want to do my octet check. So I'm going to look at each of these individually. Let's look at the fluorine on this side first. So I'm going to look at all of those, and I'm going to count 2, 4, 6, 8. That one's good. And then I'm going to check the phosphorus. It feels the effect of 2, 4, 6, 8 electrons, so that one's good. Then I can check this fluorine. 2, 4, 6, 8. That one's good. And then finally this fluorine feels the effect of all of those electrons. 2, 4, 6, 8. That one is good. So my octet check is good. We'll see. We'll see. We'll always get a way to make it work, but we'll see. Okay. So, try this one on your own. I'll start talking through it in a moment, but I want to see how many of you can work through it. Tetra represents what number? 4, absolutely. That's a common one too. How many valence electrons does carbon have? Shout it out. 4. What about hydrogen? 1, and there are 4 of them. So I am looking for a total of what? 8. Which one requires the most electrons? Carbon. It needs 4 more. Each of the hydrogen only need 1. So carbon goes in the middle, and we're going to have single bonds with each of the hydrogen. Hydrogen can only ever have single bonds, because it can only ever have the effect of 2 electrons around it. Otherwise, we're making it really unstable. We can do our check, 2, 4, 6, 8. That's good. My octet, or my di check, 2, 2, 2, 2 for my hydrogens. Carbon has the 4 bonds, so 8. Questions on that one? Okay. Moving right along. Oxygen. That's just that, right? No, why? Yeah, it is diatomic, so it's O2. Good. So, O2, that means we have 2 of our oxygens. Each of the oxygens are 6, so I'm looking for a total of 12 electrons. So I can start drawing it out. 1, 2, 3, 4, 5, ooh, and 6. 1, 2, 3, 4, 5, and 6. We'll clean it up a little bit. And we'll put a bond right there. We'll share those 2 electrons that I just erased. Oh my goodness. My board is not functioning properly. There we go. Am I done? No, why not? It's not meeting the octet rule. Good. Okay, this oxygen only has 2, 4, 6, 7. This oxygen only has 2, 4, 6, 7. Neither of them have 8 yet. So, we form a double bond. So, 2 lines represent a double bond, which are 4 electrons that are being shared. Do I have 12 electrons total?
Yeah.
Yeah, I do. Do I meet my octet rule? Yeah, I do. Each of my oxygens feel 8. So we've got a double bond. Double bond. Looks kind of like the equal sign. Those are 4 shared electrons. Next one. Nitrogen. That's right, isn't it? No, why? Yeah, it's diatomic, 2 of them, perfect. So, we have 2 nitrogens. Each nitrogen has 5 valence electrons, so we're looking for a total of 10 electrons. So I can start drawing it out. Is a single bond gonna do it? No. No. What about a double bond? No. This is our beautiful triple bond.
What's the highest bond you
Triple.
Really?
Yeah. Yep. Triple bonds are the biggest. So, or the most amount of bonds you can have between 2 atoms. They're never quadruple bonds. Good question. Okay, does it meet my total? Yeah. Does it meet my octet? Yeah. Questions yet? So again, do is a triple bond, which are 6 shared electrons, and this is our biggest, I don't want to use biggest, this is our maximum number of bonds. Between 2 atoms. Yeah.
So, like, would this be, like, the strongest bond?
Excellent question. That's what we're going to get to next. Perfect. Perfect, perfect. And indeed it is, because the bond strength, we have the shorter the bond is the stronger the bond, and we go single, double, triple. The triple is the shortest, which means it is the strongest. So the decreasing length leads to an increase in strength. And I don't know what all the little things are. There. There's more being shared. It's holding them closer together. That makes it stronger, harder to rip apart. Okay. So, dihydrogen monoxide. What do we typically call this? Water, absolutely. H2O. Go ahead, draw it out. Hopefully you have something that looks a bit like this. You may have your hydrogens across from one another. We will find out tomorrow that that is not how they would behave. At this point, it's fine. We'll find out tomorrow why we have this bent shape. Questions on water? Okay. So we've got some special cases. The octet rule is not always followed, because when we have small molecules like beryllium chloride or boron trifluoride, we don't have enough space for the unpaired electrons. And beryllium chloride we would normally think is an ionic compound. It's going to be a very polar compound. So in BF3, the fluorines would each have their 8 electrons, but the boron would only have 6 around it. And that's okay because it's so small that it couldn't hold anymore. We also have instances that we call dative or coordinate covalent bonds. Again, this could be either polar or nonpolar, where one atom donates both the electrons in a single bond. So sometimes it seems like we're doing a little bit of magic to make sure that each of them have 8. When we're doing that, when we're shifting things more than we normally would, that's what we call a coordinate covalent bond. And it's working the same as the regular single bonds, except that the 2 electrons that are being shared are coming from one species, not one from each of the species. And sometimes you'll see where it's represented so that we can see that they're both coming from one with an arrow. So rather than having, let's say, X and Y, rather than having it just like that, where both of them are coming from X, sometimes it'll show an arrow where both of them are coming from X over to the Y. So sometimes you'll see that. Okay, last one to go through, because we do have these polar molecules that are polyatomic ions, and we have to account for the fact that we have charges. So, nitrogen, there's 1 of them and they have 5 valence electrons. Hydrogen, there's 4 of them and they each have 1 valence electron. The 1 plus means that I have lost 1 electron. So -1. So we have a total of 8 electrons. Now we draw these out a little bit different as well. We put brackets around our drawing, and we put the charge outside the brackets. So I'm going to put my one that needs the most in the middle. Nitrogen needs 3 of them. The hydrogens each only need 1. And we're going to do 4 hydrogens around it. And I'm going to do my double checks. My octet rule is satisfied. Oops. Because each of the hydrogen have 2, the nitrogen has 8, and then total of 8. So my total check is good as well. What questions do you have?